Okay, so let's move on to a new concept called gravitational field strength. And obviously, since we're talking about gravitational field strength, it must be somehow related to force, because force is really the best measure of the strength that something exerts on another object. Gravitational field is a little tricky, though, because, what is a gravitational field? It's a very intangible object because it's not something that you can see. It's something that literally fills the three-dimensional space surrounding all objects that have gravitational mass. And so the gravitational field fills the space around all objects which have mass. And the importance of this idea of a field force, is that fields are what we use to explain what we call forces at a distance. That is to say that gravitational field is very different from the normal forces that we feel, like, for example, the normal force, the frictional force, the tension, the applied force. These are forces that are simply a result of two objects literally being in contact with each other. This is why it's so easy to identify those forces, because if you cannot see that they are in contact with some object, then that object is not exerting a force. For example, if I swing a mass around on a string, my hand is not exerting a force on the mass. My hand exerts a force on the string. The string exerts a force on the mass. So contact forces can only be conveyed between two objects if there is literally physical contact between them. Gravitational force is very different, because gravitational force does not require the objects to be in contact with each other. In fact, there may be vast distances, millions or even billions of miles may be separating the two objects, and yet they still feel a force as a result of this gravitational field. So the definition of the gravitational field strength is the gravitational force per unit mass, and we could add something at a point in space. So the gravitational force per unit mass, and of course we're specifically concerned with it at a particular point in space. It could be at the surface of a planet or the Earth or at some object, or it doesn't have to be. It could be thousands or millions or billions of miles away from the object. We can calculate how much force is exerted on 1 unit mass. Now, per unit mass means divide by the mass. Divide by a unit mass. So this would be the gravitational force divided by m. But remember, the gravitational force is g m1 m2 over r squared, and then I would divide all of that by m. Now, obviously, we have to think carefully about which m am I talking about. Well, in this case, we're talking about the little m. Remember, the convention is that the big m first, the big mass first, and then the little mass. So I'm saying per unit mass, I'm saying what is the gravitational force on a 1 kilogram mass. I'm not talking about the gravitational force that 1 kilogram mass exerts. I'm saying that there is some other object which is exerting a gravitational force on that 1 kilogram mass. So the correct mass to divide by is m2, and what this is going to give me is the gravitational field strength at some point in space because of mass 1. Mass 1 is the guy who is originating, who is causing the gravitational force. And I'm going to figure out his gravitational field strength at various points in space. Now, when we do this division, you will find that the masses cancel, so that I end up with this expression, g m1 over r squared. Now, hopefully that looks very familiar to you, because let me remind you from a previous lecture, we already found that force, that combination of variables, g m1 over r squared. That was the acceleration due to gravity at a particular point in space. So this is kind of an interesting thing. It turns out gravitational field strength and the acceleration due to gravity are the same thing. So when I calculate this, remember this was force divided by mass. That would be the number of newtons per kilogram. But it's also the same thing as the number of meters per second squared. Now let's just verify that that really is true. If I have a newton per kilogram, and a newton is a kilogram meter per second squared. So remember, newtons are mass times acceleration. Mass is in kilograms, acceleration is in meters per second squared, and then I'm going to multiply that by kilograms per kilogram. They go away, and I end up with meters per second squared. So it turns out they are the same units. Now here's a little bit of a trick that you kind of need to keep straight. It depends on how you're making reference to it. If I ask you what is the gravitational field strength, I'm looking for you to tell me the number of newtons per kilogram. If I ask you what's the acceleration of gravity at a particular point in space, I'm asking you for meters per second squared. But what you should recognize is that although the units look different, the number will be exactly the same because it is exactly the same formula. So for this reason, we use the letter little g to represent not only the gravitational acceleration at a particular point in space, it also represents the gravitational field strength. And remember, gravitational field strength is the force per unit mass exerted on an object. The force per unit mass. So, for example, since we've already done the Jupiter as an example, let's take a look at the Moon, for example. So let's calculate the gravitational field strength on the surface of the Moon. Now, what will I need to make that calculation? I will need to know the mass of the Moon, and since I'm talking about at the surface, then I'll need to know what is the distance between the surface of the Moon and the center of the Moon. So it turns out that the mass of the Moon, just to remind you, these are all things that we can look up in the table in the back of the book, and according to Appendix 3, the mass of the Moon is 7.35 times 10 to the 22nd. And the radius of the Moon is 1.74 times 10 to the 6th meters. Okay. So let's go ahead and calculate the gravitational field strength at the surface of the Moon. This would be little g is equal to big G, mass of the Moon, divided by the radius of the Moon, and that's going to be 6.667 times 10 to the minus 11, times the mass of the Moon, 7.35 times 10 to the 22nd kilograms, divided by the radius, I'm sorry, do that a lot, don't I? Sorry, that's the radius squared. Yeah, definitely do not forget that. 1.74 times 10 to the 6th squared. Okay, so let's go ahead and make that calculation. 6.667 to the negative 11th times 7.35 to the 22nd power equals divided by 1.74 to the 6th squared, and that gives me little g is 1.619 newtons per kilogram. Now this is the nice little trick about making the calculation of gravitational field strength. That is also the acceleration of gravity. So you kind of kill two birds with one stone. You can find the gravitational field strength at a particular point, then simultaneously you have also found the acceleration of gravity, 1.619 meters per second squared. So think about the Earth. The Earth has an acceleration of 9.8 meters per second squared. That means that also, therefore, it has a gravitational field strength of 9.8 newtons per kilogram. And so we can calculate how many G's, that is to say that G's, this is the variable G's, but we can also use G as the units. And in this case, we would divide this guy simply by the value of gravity at the surface of the Earth. 1.619 divided by 9.80. And I get approximately 0.165, or in other words, about 16.5% of the value at the surface of the Earth. I could do the same thing. If you remember that in previous calculation, we had calculated the gravitational field strength, the gravitational acceleration at the surface of Jupiter, 26.5 meters per second squared, but now you should also recognize, I could have also said that the gravitational field strength was 26.5 newtons per kilogram. Okay? So it's kind of a nice little trick where gravitational acceleration and gravitational field strength are exactly the same thing. So it turns out that the gravity at the surface of the moon is approximately 1/6 of the value that it is at the surface of the Earth.